Good morning, students. Today our new topic is solubility of a gas in liquid. So we know that many gases dissolve in water. The gases are dissolved in water, like oxygen and nitrogen, oxygen, nitrogen. So like these gases are dissolved in water. Okay. And that hydrogen chloride gas is highly soluble in water. That hydrogen chloride gas is highly soluble in water. And solubility of gases in liquid is generally affected by pressure and temperature. So the solubility of gases is affected by temperature and pressure. So with the increasing of pressure, the solubility also increases. With the increasing of pressure, the solubility also increases. So let me take one example for solubility of gas in liquid. So see here, I'm taking a cylinder. So in that cylinder, I'm taking the solvent. It may be water. Just you assume that it is a water. So this is the solvent, and above that solvent we have gas molecules. That gas molecules indicated by red dots, and that solvent is indicated by blue dots. And here the temperature is T1. And this one is the piston, and above that piston I'm taking a weight W1. So here the upper part is a gaseous system and the lower part is a solution, because in this lower part we have solvent and solute particles also. We have solvent and solute, so that's why it is called solution. So the upper part is a solute system and the lower part is a solution. Solute system means it is a gaseous system, so above that solution we have gas molecules. Assume that this system to be in dynamic equilibrium state. That means the rate of gaseous molecules entering into the solution and leaving the solution, is same. Means how many solute particles enter into the solution, the same number of solute particles, means the gas particles, leaving the solution. For example, 6 solute gas particles enter into the solution. Same number of solute particles means 6 gas particles leaving the solution. Now here, increase the pressure over the solution, it will increase the number of gas molecules per unit volume over that solution. If I take a unit volume, so this is I'm taking as a unit volume. So in that unit volume we have only one gas particle. Let me assume that there is a one gas particle in a unit volume over that solution. So here, if you increase the pressure over the solution, it will increase the number of gas molecules per unit volume over that solution. So for increasing pressure, what we have to do here? So we have to take more weights above that piston. If you increase that weights above that piston, so then the piston comes down, means the volume decreases. If the volume decreases, automatically the pressure also increases. So above that piston, I am taking three weights. For example, here I am taking a W1 weight, means for example I am taking 10 grams of weight. If I increase the weight above that piston, means here I am taking W1, means here 10 grams and here 10 grams and 10 grams, total 30 grams, means here I increase the weight. If I increase the weight above the piston, then the piston will comes down. Means here, see here, this is the piston position in first stage. So this is the piston position in second stage. So here the volume is high, but here the volume is low. So with the increasing of weight on that piston, the volume will be decreases. So here there is no change in temperature. Here T1 temperature and here also T1 temperature. But there is a change in pressure. So here volume more, the pressure is P1. Then I increase the weight on that piston. So then the piston comes down. Means here the volume decreases. So if the volume decreases, automatically the pressure will be increases. So the pressure will be change. So the pressure is P2. So there is a change in pressure. So the changed pressure is P2. So in first stage we have less pressure. In second stage we have more pressure. So here the pressure has been increased. So the distance between the gas molecules will be decreases. So here if you observe that unit volume, the unit volume increases. So here I consider it as a unit volume. So in first stage, so here in a unit volume we have only one gas particle or one gas molecule. But after increasing the pressure in one unit volume, so there are three gas molecules or three gas particles. So with the increasing of pressure, the unit volume increases. The number of particles increases in a unit volume. So the number of gas molecules are increased above the surface of that solvent. So more number of gas molecules are enter into the solution. Now increase the pressure over the solution. It will increase the number of gas molecules per unit volume over that solution, and also increase the rate of gases molecules are striking the surface of the solution to enter into the solution. So here the more number of gas particles are enter into the solution. So thus its solubility increases. So with the increasing of pressure, the solubility will be increases. So the solubility of gas in a liquid increases with the increasing of pressure. So if you increase the pressure, so the solubility of the gas in a liquid will be increases. So here solubility is directly proportional to pressure. So in the solubility of a gas in liquid, so the solubility is directly proportional to pressure. So with the increasing of pressure, the solubility of the gas in a liquid will be increases. Next one, Henry's law. So the Henry's law is the definition of Henry's law: a quantitative relation between the pressure and solubility. Of a gas in a solvent is known as Henry's law. So a quantitative relation between the pressure and solubility of a gas in a solvent. It is known as Henry's law. And this last statement is at a constant temperature. The temperature is constant. So temperature constant. So at constant temperature, the solubility of a gas in a liquid, the solubility of a gas in liquid is directly proportional to the partial pressure, of a gas present above the surface of the liquid or solution. So this is the Henry's law statement. So the Henry's law statement is at constant temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas present above the surface of the liquid or solution. So this is the Henry's law statement. So already we discussed that in previous one, the solubility is directly proportional to pressure. So if the pressure increases, the solubility also be increases. So here, instead of solubility, if you take mole fraction, so the Henry's law statement turn to the partial pressure of gas in vapor phase. The partial pressure of gas in vapor phase is directly proportional to the mole fraction in the solution. So this is the Henry's law statement with a mole fraction. Instead of that solubility, if you use that mole fraction, so the Henry's law statement turn to the partial pressure of a gas in a vapor phase is directly proportional to the mole fraction in the solution. So we know that mole fraction. So mole fraction is a ratio between the number of moles of one component and the total number of moles of all components. So instead of solubility, we have taken that mole fraction. So here, if you take one constant, so P is equal to, if you take one constant kh is the Henry's law constant, kh and mole fraction x. So P is equal to kh into x. So here kh is a Henry's law constant. And here the kh values depending upon the nature of gas. Because different gases having a different kh values. So at the same temperature, let me take one graph. So on y-axis I am taking the partial pressure, that pressure in torr, the units are torr. So on x-axis I am taking the mole fraction of HCl gas in cyclohexane. Cyclohexane is the solvent and HCl gas is a solute. That HCl gas in cyclohexane, mole fraction of HCl gas in cyclohexane. So here with the increasing of partial pressure, the mole fraction will be increases. If I take here the mole fraction is 0.01. So here I am taking the pressure is only 500 torr. So if you increase the pressure at 1000 torr, the value is 0.02. the mole fraction is 0.02. Means with the increasing of partial pressure, the mole fraction will be increases. So here the Henry's law statement fulfilled. So P is directly proportional to mole fraction. Pressure is directly proportional to mole fraction. Means if the pressure increases, the mole fraction also be increases. So with the increasing of pressure, the mole fraction increases. And here the higher kh value and lower solubility. Means with high kh value, the solubility will be low. So if there is more kh value, there is a less solubility of the gas in liquid. So here let me take two gases N2 and O2. So that kh values for N2 and O2 increases. The kh values increases with the increasing of temperature increases. So with the increasing of temperature, that N2 and O2 gas kh values will be increases, and the solubility of gases increases the decreasing of temperature. Means if you decrease the temperature, the solubility of the gases increases. For example, the cold water contain more O2 gas. Cold water contain more O2 gas. Means in that water we have more O2 gas at low temperature. If you increase the temperature, means that warm water contain less O2 gas. Warm water contain less O2 gas. So cold water contain more O2 gas, and warm water contain less O2 gas. So here temperature less and here temperature more. So at less temperature, the solubility of O2 increases. At high temperature, the solubility of O2 decreases. So the solubility increases with the decreasing of temperature. With the decreasing of temperature, solubility increases. The relationship high kh and lower solubility. So solubility is inversely proportional to kh. Inversely proportional to kh. And the kh values increases with the temperature increases. With temperature increases, the kh value increases. So here temperature is directly proportional to kh, and here solubility increases with the decrease the temperature. So solubility is inversely proportional to temperature. So there are three relationships. Solubility in inversely proportional to kh. If kh more, the solubility will be less. If solubility more, the kh will be less. And temperature is directly proportional to kh. If temperature is more, the kh also be more. And the solubility is inversely proportional to temperature. If temperature less, the solubility will be more. If the temperature more, the solubility will be less. So this is about solubility of gas in liquid and Henry's law. And next one, Henry's law applications. So here, to increase the solubility of CO2, in the soft drinks and soda water. Soft drinks and soda water. The bottle is sealed under high pressure. High pressure. To increase the solubility of CO2 in soft drinks and soda water, the bottle is sealed under high pressure. And we know that thumbs up and 7 up, some of that soft drinks. So in that soft drinks, there is more pressure. So because of that more pressure, the CO2 solubility increases in that soft drinks. So that scuba divers breathing the air at high pressure under the water with increase the pressure increases the solubility of the gases in the blood. So when scuba divers come towards the surface and the pressure gradually decreases, this releases the dissolved gases. It leads to formation of bubbles of N2, bubbles of N2 in the blood. And this N2 bubbles blocks the capillaries. That N2 bubbles blocks the capillaries. Capillaries and creates the bubbles of N2, creates the bubbles of N2 in the blood, and it is called bends, and it is dangerous to the life. So when the scuba divers breathing the air at high pressure under the water, increase the pressure increases the solubility of the gases in the blood. So when the scuba divers come towards the surface, the pressure gradually decreases, and due to that decrease in the pressure, it releases the dissolved gases and leads to formation of bubbles of N2 in the blood. So that N2 bubbles blocks the capillaries, and creates the bubbles of N2 in the blood is called bends. And this formation of bends is dangerous to the life. So to avoid that bends, so the scuba divers using that tanks which is contain the gas, and that gas or that air diluted with helium, diluted with helium. So in that tank the helium percentage is 11.7 percentage and N2% is 56.2%, then O2% is 32.1%. So the gas which is present in the tank will be diluted. Due to that dilution of gas is avoid to the formation of bends. And at high altitude, means the hill stations, the partial pressure of O2, is less than that at the ground level. So there is a less percentage of O2 when we compare with the O2 where in the ground level. So this leads to low concentration of O2 in the blood. So low blood oxygen causes unable to think clearly. So means the persons cannot think clearly. So that behavior is called anoxia. Anoxia. So the low percent of O2 in the blood causes anoxia. So at high altitude means in hill stations, the partial pressure of O2 is less than that at the ground level. So this leads to low concentration of the O2 in the blood. So low blood oxygen causes climbers to become weak and unable to think clearly. So the behavior of unable to think clearly is called anoxia. And next one, effect of temperature. So the solubility of gases in liquids, solubility of gases in liquids decreases with the increase in temperature, with the increase in temperature when dissolution is exothermic, when the dissolution is exothermic and the solubility gases in liquids, the solubility of gases in liquids increases with increase in temperature when the dissolution is endothermic. The solubility of gases in liquids decreases with the increase in temperature when the dissolution is exothermic, and the solubility of gases in liquids increases with the increase in temperature when the dissolution is endothermic. So this is the temperature effect of the solubility of gases in liquids.